Hello everyone, and in this video today I will talk about quaternions. I have talked about 3 by 3 matrix, 4 by 4 matrix, and quaternion is the next step after those videos. And this is a way how we calculate rotations in any 3D software, and it is a more efficient way than Euler angles. And I will also cover what are Euler angles and how we store those rotations in matrix. And I will break this quaternion down, and I have created this simple way to understand the very fundamental of the quaternions. And this will be a two video thing. Quaternions, I will cover the what are quaternions and what is the theory of quaternions in the first video, and second video I will use this quaternion and I will use that in Houdini, and I will do some rotations with this. So let's first talk about what are quaternions. I'll just open PureRef and I will talk about these 4 by 4 matrix, quaternions conversion, gimbal lock, how rotation stored in 4 by 4 matrix, Euler angles, quaternion breakdowns, and uh, and related to these topics. So first, what is quaternions? I will not start with directly with this. I will start with matrix. And I have created, I guess, 3 videos about matrix, and I will just cover like the 4 by 4 matrix real quick. And we need this to understand the quaternions, because if you can merge the gap between matrix and quaternions, then it will be more easier for you that to understand this. I will create a note. I will draw something. So I will just create here a matrix. And this is an identity matrix. So I will just say 1, 0, 0, and tx, and I will say 0, 1, 0, ty, and I will say 0, 0, 1, tz. So what is happening here? This is identity matrix, and this is perfectly aligned with the world matrix, and you see the x-axis of the object is facing in the x-axis of the world, and y-axis in the y-axis of the world, and z in the z-axis of the world. And if when I'm saying here x, y, and z, this is uh, this is the direction based on the world. Here this is like not a vector, this is just to represent the direction like this. See, this is the x component of the object, right? And where this is facing, and it is facing in the x direction of the world. So we represent this by like this. If I'm saying that the x is 1, y is 0, and z is, let's say, 0, that means this axis is facing in the x direction, right? And when I said axis, I didn't say vector. I will just clear this out too. So I have this 4 by 4 matrix, right? And when I say this 3 by 3, this part, I will just say color, different color. When I'm saying that this part is for rotation, scale, and orientation, I talked about this, right? And when I talked about this in the matrix 3 by 3 matrix, I told you about that how we store rotation here, and I won't go in depth here about this rotation, but I will talk about what are different types of rotation and how the Euler and this quaternions is like have differences in between them. So when we do some basic rotation in 3D, we use Euler angles. We use Euler angles. We use 3 axes, and we do this in an order. Like if I have this f, right, this is my x, this is my y, this is my z. So if I'm saying something like I want to rotate this cube along z-axis in this rotation, and I want to make this cube in a particular rotation. Let's say I want to rotate this cube in this rotation. So to get to this point, get to this rotation, what this cube will do, there is this method, and we call this gimbal method. So first what will happen, there is this order to reach up to that rotation. So if to reach that rotation, we need to go through these axial rotations. So what do I mean by that? If I want to rotate this object in x-axis along the x-axis, this is the x-axis, and I want to rotate this along this x-axis, that means we just can rotate this. If I'm saying that I want to rotate this in like by 30 degrees, right, and I'm taking this angle in radians, but this all will be converted in 0 to 1, and that's why it is a bit more complicated, but just forget about that right for now. So here we have x, which is, I'm saying I want to rotate in 30 degrees, or if I'm saying I want to rotate the object along z-axis. So what will happen when you rotate that along z-axis? It will do this rotation, and this y will be here, right, and this y will be here, and this x will come to here, but this z will stay the same, right? So this angle, we call this theta, and this angle will be calculated by trigonometry. And trigonometry all about curves. Trigonometry is all about curves, how you calculate these angles, right? And we use cosines and sines, but we don't need to do the calculations by ourselves. We just need to understand what are Euler angles. And when I said if I want to go from one orientation is like where the object is facing, and now if you want to change, it's like if you want to rotate that object, and if it has something like, if the object is facing the x axis, that means it has its orientation, and when the object is facing y axis, now it has its own orientation. And when you convert one orientation to another, when you rotate your object, so it is going from one orientation to another orientation, and we call this interpolation. And when I do interpolation, there are two ways any 3D software store that interpolation. We need data, right? We need to store that rotation in a data form. So Euler angles is a data form in that case. So it will first rotate the object as the base of x-axis, then it will do as y-axis, and it will do as z-axis. In this case, order matters. I cannot say that rotate y in same 30 degrees as I did with 30 degrees in x. It will be a different rotation. If you just imagine, and if you just pause a bit here, and if you think about this, and you say like, if I want this object, like this object to go in this rotation, right? So what will happen? First it will do in this, and that it will do in the y rotation, y axle rotation, and you will see your object, it will be here. So it goes from this to this. And if I do the same but with a different rotation, like if I'm saying I want to do first this, then do this, right? So this degree is not same as this degree, right? This can be higher. So if you do something like this, so in this case, there are many ways to go to that simple rotation. There are so many different orders that we use. First we can say I want to rotate in x, then I want to rotate in y, then I want to rotate in z. So to reach orientation, like to reach at one orientation, you need to perform this gimbal rotations. You cannot go there by one rotation. You cannot go by one rotation. That's our Euler angles. So you are using simply 3 rotations to reach a certain orientation. That's why we have Euler angles, and we have different type of methods here. Here you can say I want to rotate it first at x, then y, then z, or you can say y, x, z. And if I open Houdini, you will see inside this, just ignore this, just geo rubber toy. And if you see this, if I drop a transform every time, if I drop this transform node, you will see we have these different orders of this rotation. So here we are using Euler angles. That means if I want to rotate this, I will say this, and I will say this, and I will say this. I cannot reach this point, right? I cannot reach this orientation if I say something like this. You see, it's just converted into another orientation. You see, if I change this, these values are same, but we are not having the same orientation, because here order matters. If you are going into this orientation by this xyz order, then you need to follow the x, y, and z. You cannot follow another another order to get the same rotation. Then you need to change these values in order to get there. I hope you understand this, right? So we call these Euler angles. We are using something like this. And when I just make it this default, and you see when I click this, you see this gimbal. That's how all these rotations are happening. This is along z axis, right? We are rotating it along the x axis, sorry, and here I am rotating it along the z axis, and here I am rotating along the y axis, right? And I want to just say it again that positive z axis, we in Houdini, is considered front, so it will be facing positive z axis by default. That's why it's considered as front in Houdini. So you see this we can rotate objects by this method, and we can store data. Like we can store the first, it moved in x, then y, and then z, right? This is the first method of rotation. It has its own consequences. You see in this viewport, you see you are not having any issues. Like you can make any orientation here you want, right? Because first, you are not animating this object. You are not making it from one orientation, you are not animating it from one orientation to another orientation. And when you animate something, you need to consider the base values first. If I'm saying this object is here, right? So you know we have our base value. So it is at 0, 0, 0. We have no rotations here, right? And when I rotate this here, the values changed, right? So we know that we went from 0 to some values in this 3D space. And we store those values as data, right? That's why we can store those animations. And here is the real different and difficult case. Here is this scenario where we hit something, and I will tell you what we hit. So when I am rotating this object in these direction, you see this gimbal is also updating, and this not happens when we store data. This is just the viewport thing here. This is just to make the beginner user, those users who are beginner in this, just easy for them to move the object. But when you animate something, on when you do some heavy complex rotations, you cannot have this gimbal updating with your object, because you need a fixed base. You need a base that can say that the base is here and you are now moving around, so you can have the data. We are at 0 first, then we moved 1, then we moved 2, so we are rotating as a base. If I'm saying that the base is this, right? This is about this viewport. If I'm saying that this is the base, now I have moved the geometry and the base has shifted with it. So the gimbal is also shifted with this. You see, the gimbal is also rotating. That's why this is just for the viewport, to make it easy for the users to just rotate the objects in the viewport. Second thing, we are not animating, right? And I will just tell you, when we animate something, this is not This is not being updated when with the rotation. This is fixed, and you can do that. So how, there is this option. If I say rotate, and you have this pivot mode. Okay, I'm not object, I want the transformation, right? And you have this pivot mode. So what has happened here, now it is acting as how we store data here. I will just make this small so you can understand this. Now this gimbal won't update because now we have a base, and everything we do will be stored as values according to this base. So we know that what was the initial values and what are the final values, so we can store that animation data, right? So when I rotate this, you see we are rotating it, but the gimbal is not updating. The gimbal is fixed. The gimbal is fixed, but we are like rotating in this axis. We are rotating in this axis, but here is the catch, the biggest catch here. When you say I want to do something like, okay, this is updating, gimbal mode, sorry, what I was doing. Okay, you see, I accidentally said that the pivot mode, but it was the gimbal mode, my bad. So we have the gimbal mode now. So it is happening as we animate object, and now you see these things are not, like, the gimbal is not updating. You see the x-axis is still, but when I said what is this? Okay, this is like really stupid sometimes. I hate this software sometimes, to be honest. See, now I'm not getting that. Not this. Maybe show me, you can. Why I'm not seeing that? The gimbal mode, when I turn the gimbal mode off, you will see now the x-axis is updating with this geometry, and when I say gimbal mode, now this x-axis will be fixed. The real drawback of this gimbal mode, and it happens all the time if you use Euler angles, and if you are doing some complex rotations, then you will definitely hit this. So what is happening when you hit this? When I'm saying something like this is updating, wait a second, you will see I want to rotate it in this direction or in this direction. Yes, let's say I want to rotate this along the z-axis, right? And when you hit 90° along z-axis, you will see these two axes, now x and this y-axis doing the same rotation. When I do this, for this here in this orientation, the x-axis is doing this rotation, right? And when I say this, now the x-axis is doing the same as the x-axis doing the same rotation. This is we call gimbal lock, right? And this you cannot see in here in this viewport thing, right? You see when you animate something, when you rotate an object, so you see those numbers sometimes just merge, combine, or do this weird things. So that's why we don't use this method as complex rotation, but for viewport we can use this method, but for complex rotations or animations we don't use this method. To solve this method, there was a scientist, it was a mathematician, and he created this concept of Quaternions, and it was way before when these 3D softwares like use rotations, right? So what he created this Quaternion method, and by Quaternion, what he said, he didn't just fix this issue like we are facing right now in Euler angles. We also use quaternions in jet fighters. They're they're when we store those rotation data of a jet and airplanes, we use in satellites, we use in space programs. Everywhere this quaternion concept used when we talk about rotations, right? And the crucial thing here, it is a bit more complicated to like imagine, so I will just make it super simple for you. And okay, just focus on this now. I will say draw something, right? So as are Euler angles use these rotations. What he did, if I have something like this, right? So what he did, this quaternion first is a method to store the rotation data. Rotation data, right? And this rotation data is now being stored in this vector 4 vector data, right? Now 4 component vectors, sorry. Now this data form is stored in this 4 component vector, and this is not stored in matrix, right? This is not stored in matrix. It is as a separate data. It is act as separate rotational data, and I will talk about the connection of matrix and this. But for this is a 4 component vector which stores this rotation value. And when I'm saying I have this object, right, I have this object and I want to rotate this, so I have method. I want to make this something a weird rotation. I want to go here, right? So what will happen with the Euler method? You will say I will rotate in x, in y or z, or any other order you want you to reach this point. But quaternion use a 4th axle, right, on which you rotate that object to reach that orientation with single go. You don't need to go to reach here, you just reach there, or you just reach there, or you just reach there. So what is happening here, to reach there you cannot use these 3 axes, you need another axis, and that's the imaginary axis. Now you are rotating on, right? So this is just an imaginary axis. It's the 4th axis on which this rotation is happening. If I'm saying I'm rotating along y, so you will do this rotation. When I'm saying I am rotating along x, you will do like this rotation. What this rotation, or this rotation. When I'm saying z, you will do the front rotation. And I'm saying I have this axis which is imaginary and it will do this rotation. So maybe this axis is going in this direction and you will do this rotation to reach this point without reaching these 2 axes. You will in one go, you will rotate in this axis and you will reach here. So this is simple. I will just do it again. This is z, this is x, this is y. Quaternion use the 4th imaginary axis to reach, or it can be, let's say I want this axis and I want this rotation, and you can just draw this rotation or any rotation you want. So this is a sphere. Okay, first let's talk about circle, right? So you can understand this better. This is a circle, and let's say you only have 2 axes, right? But I created let's say these two axes, right? One rotation can happen here and one rotation can happen here. So I am saying that now the object is rotating being along this axis, so it will go here and you will get this theta, right? This angle of this rotation, right? And this angle of rotation will be calculated by trigonometry, because here we are using curves. So this rotation is happening and it is not in a straight line, it is curved. So we use trigonometry here and it is all math. But the main thing here is that we don't need to understand how these calculations are happening, because Houdini will do its on its own behind the scenes, right? We just need to understand how these how these concepts work. So we will get this theta, right? The rotation is happening. And the cool thing here is, when you rotate along z axis or any other axis, the other two will move. So other two's data will change, right? It will be similar. The z data will be similar. So the rotation will happen along the z axis, but the y and x data will change. And to manually calculate the data by our hand, it's very complicated, to be honest. It's very complicated, because we need cosines, sines, and we need to, we just need to know this 2D circle, math. We just need to know that. I can just say, for this example, I will just say, I will create a matrix. I will create a matrix now, and I will say, let's say we are rotating along the z-axis, right? So this y will go here, this x will go here, right? And this y will go here. So what will be this angle? And whatever this angle will be, we need to store that in 0 to 1, because this is where the y is facing. This is +1, this is +1, this is -1, this is -1. So y here will face, it will be around 0.7, and this is 45. So you will get this 0.7 value. You just need to understand that how these values are created, how these values are being calculated. And here we use sines and cosines because we are working with curves, circles, right? And we are calculating the angles here. And also, now we know that this is a 2D thing, right? We are talking about 2D, but we have also had z-axis, but this is a bit more easy to comprehend, because we are only doing it's simple single rotation like this, right? But if I'm saying I have this sphere, right, and you have these axes, and I will create a random axis and rotate that object along that axis, and it will be then more complicated to just calculate those values by our hand, right? So I will just break down the quaternion, I will break down the quaternion, attribute and what it has. So as I just covered that, we need an imaginary axis, right? So we have x, y, and z. This will give you the imaginary axis that we are talking about, right? Where that is facing. Simple. It will go through the pivot of that object, and it will say whatever that axis will be, the object will rotate along that axis. And also, you need the fourth component, which is w. And here w is not this angle, the angle by the rotation is happening, no, but yes, it is based on that angle. So w here equals to cos theta divided by 2, and theta here is the angle of that rotation. So how they came up with this formula? They are mathematicians. I'm not a mathematician and I don't know how this came from, and I don't want to really understand how this came from, to be honest, because if I go into this, then I need to like understand many other mathematical concepts which we don't need, because everything will be happening behind the scenes and Houdini will be doing this heavy mathematical work, you know, like for us. So we don't need to like really understand, but you know that we have two things. This W value will be based on this theta. Theta is the angle of that rotation, and XYZ is the direction of that axis, like where is that axis is going through. If I'm saying that that axis is going, this is our object, and that imaginary axis is going in this, right? We have X, we have Y, and we have this Z. This imaginary axis is this, right? So we need to say where is this angle of, where is this axial rotation is happening from. So we need to define this, and this definition will be here. This data will be stored here, and the angle of rotation, this W will get when you will know the angle of rotation, the angle of rotation that the rotation is happening on, right? So you understand two things. Quaternions is a type of rotation, right? It's a type of rotation data that we store, and there is no chance of hitting gimbal lock because you are just doing one rotation on one single axis. So, and this axis is the imaginary axis, and we need that axis, wait a second, and we need that axis to do the rotation, right? So we know that two things now. We know that quaternions, and we know how Euler angle works and how quaternion works, right? But when I have this object, when I was talking about the 4x4 matrix, I talked about how that 4x4 matrix communicates with point components, point vector components, and how it update the point according to that metric data, and what point have it has homogeneous coordinates, right? And matrix has 4x4 matrix has its scale, rotation, and its translation also, right? And its orientation. And rotation is happening in matrix, it is Euler angles. Like we have the matrix, but the rotation in matrix is Euler angles. And when we are doing quaternion rotations, we are doing the rotations, but the database is there is quaternions. That means the quaternion data will be converted into matrix, and it will get this updated. This is just values. You can change these values by Euler angles. You can change these values by quaternions. You just have values, right? So quaternions can be transformed into matrix. Matrix data, this matrix rotational data, can be transformed into quaternions. So what will happen? It will look at this data, right? It will look at this data, X, Y, and Z data, this 3x3 matrix data, and that data will be converted into one axial rotation, and that data will give you X, Y, Z, and W. And W, inside W you will get theta, the angle of rotation. But this XYZ will give you the axle on which that rotation is happening. So you know that we have quaternions. You can rotate objects by quaternions. You can then convert that quaternion into matrix, and then that matrix will define everything. And when I was talking about the 4x4 matrix, I talked about how object matrix communicate with vectors, with the vectors that are on points like normal, or their p position, and this p position will give you its position, and it will also give you its direction, the point direction. So, and here we have W. I talked about this. W0 means we are only taking direction, and W equals to 1. That means we are also translating that point according to this object matrix. So if we rotate or update or scale that object, these points will also get updated to do that transformation, right? So now you know that if you want to rotate an object, you can store that data into two forms: Euler angles, second quaternions. Quaternions can be then transformed into matrix, and then those matrix can be multiplied by the object homogeneous coordinates to points homogeneous coordinates to get that to update those points according to that transformation that you did with the quaternion, right? You can do the same. You can go back and forth. You can transform object quaternions into matrix, matrix into quaternions, and you will get your desired result. So we will know this. And what I have to cover: quaternion magnitude. And this is something like x square plus y square equals to 1. This is just simple trigonometry. We don't need to understand this. Maybe for someday later we know this, but this is a mathematical thing, right? We don't need to calculate it by hand. Where they live. Okay, so quaternions, these are points. This is our curve. Let's say curve. Here these are points. You know about p scale, right? Like p scale, quaternions are attribute orient, and they have four components: x, y, z, and w. This x, y, z will give you its axle of rotation, and w will give you its theta. And w, you know what is w? W is this. This is theta divided by 2. So these points can have orientation p scale. So whatever object you will copy here, it will get this orient. What will happen? This orient attribute will convert it into matrix. That matrix will be multiplied by this object matrix. Then object matrix will be multiplied by point homogeneous coordinates, and you will get the object updated on these points. So you can transform that object by this homogeneous, by this quaternion, right? Quaternion rotational data, and you can have that object rotated wherever you want, however you want, by this quaternion, and there will be no chance of hitting gimbal lock, right? So this is how they live, right? Quaternions can live on objects, but when when you store that rotational data into objects, you can store that as quaternions, you can store that as matrix. So you can store the rotational data into two forms. You don't need to worry about too much about that. So it can live on points, it can live on objects, and it can live on geometry containers. You just rotating something along an axis with quaternions, and quaternions have two things: the axle of rotation and the w, which will give you the value of that the angle of rotation, right? So you can just rotate that whole container along an axis, and you can store that into quaternions. And what I have covered gimbal lock, I have covered 4x4 matrix quaternion conversions. You can convert that, and we will talk about the conversion code in the next part. This was just the fundamentals of how this and how rotation is stored in the 4x4 matrix and Euler angles. I've talked about this here. So I hope you understand this, because this quaternion concept is very complicated, and it took me a while to understand this concept and to come up with this theory to make you understand it better, and to make myself understand this concept better. And there are a lot of things, how these values, how we can store that data, how we can store that same data. This is the imaginary axis, and this data that this theta is w, and w here is theta divided by 2 cos. But I need to understand that how the values are being converted, because it is a bit complicated, imaginary axis and those values. But maybe when I will come with another video about this quaternion, then I will have those answers, I probably hope. and I will probably have, and I will come with some examples also. So I guess this is it for this video, and I will see you in the next one with another concept. Bye bye.